exchangers. This topic introduces the basic concept of a heat exchanger as a device to transfer heat between two fluids without mixing them. Heat exchangers are key components in power plants, cooling systems, and industrial processes. The main focus of this chapter is to understand the role of heat exchangers in energy conversion systems. This concept becomes the foundation for later thermal performance analysis. The discussion is always linked to real engineering applications.
Lesson Plan: Heat Transfer. This section shows the position of the heat exchanger topic within the overall heat transfer course. The chapter order indicates that heat exchangers are discussed after conduction, convection, and radiation. This emphasizes that heat exchangers are an integrated application of all heat transfer modes. Students are expected to already have the fundamental concepts. Therefore, the analysis here is applied and systematic. Learning Outcome. This section explains the competencies that should be achieved after studying this chapter. Students are expected to recognize and classify different types of heat exchangers. They should also be able to perform energy analysis and understand the LMTD and effectiveness NTU methods. Fouling and overall heat transfer coefficient are also important topics. All these outcomes aim to enable students to analyze and select heat exchangers rationally. Parallel versus counterflow heat exchanger. Flow configuration strongly affects heat exchanger performance, especially the temperature difference distribution along the length. In parallel flow, both fluids enter from the same side, causing the temperature difference to drop quickly. In counterflow, fluids move in opposite directions, so the temperature difference can be maintained higher. This makes counterflow thermally more efficient. This comparison forms the basis for configuration selection in design. Gas to liquid heat exchanger. This type of heat exchanger is widely used in cooling and HVAC systems due to its compact design. Its main function is to transfer heat between a gas refrigerant and a liquid coolant. The compact size allows installation in limited spaces without sacrificing performance. Heat transfer efficiency is the main design consideration. This example shows how heat exchanger concepts are applied in daily life. Printed circuit heat exchanger core. Printed circuit heat exchangers show how microchannel technology can enhance heat transfer intensity. With very small channels, the surface area per volume becomes very large. This makes the device highly efficient for high pressure and high temperature applications. It is widely used in energy and chemical process industries. This example emphasizes the role of design innovation in improving thermal performance. Check your understanding. Number 1. This section serves as a short pause to check understanding of the previous concept. The question focuses on the relationship between compact design and heat transfer performance. The goal is to ensure students grasp the main message from the printed circuit heat exchanger example. Such evaluations help reinforce key concepts. After this, the discussion returns to the main material. Cross-flow heat exchanger configurations. In cross-flow configurations, one or both fluids can be mixed or unmixed. Unmixed conditions generally provide better thermal performance. This is because the temperature gradient can be maintained more stably. Tube arrangement and flow paths strongly influence this behavior. This configuration is often chosen for systems requiring compact design. Shell and tube heat exchanger. A shell and tube heat exchanger consists of a tube bundle inside a shell to facilitate heat transfer between two fluids. The shell side and tube side fluids flow separately so that no mixing occurs. Baffles are used to direct the shell side flow to increase turbulence and the heat transfer coefficient. The front end and rear end headers manage the flow distribution on the tube side. This design is very popular because it is robust, flexible, and easy to maintain. Correct answer: B.
to improve turbulence and direct shell side fluid flow across the tubes for better heat transfer. Explanation of incorrect options. A. To provide structural support for the tube bundle during fluid flow. While baffles may provide incidental support, their primary role is to enhance heat transfer by improving fluid turbulence and directing shell side flow. C. To prevent mixing of tube side and shell side fluids by creating separate flow paths. This is incorrect because the separation of fluids is achieved by the design of the heat exchanger itself, not by the baffles. D. To collect and distribute tube side fluid at the front end and rear end of the exchanger. This is incorrect, as this function is performed by the headers, not the baffles.
Multipass shell and tube heat exchanger. Multipass configurations are used to improve thermal performance by forcing the fluid to pass through the exchanger multiple times. With more than one pass, the average temperature difference can be maintained at a higher level. This increases the total heat transfer without increasing the size of the device. One shell pass and two shell pass arrangements are common examples. This concept shows how flow arrangement can improve system efficiency.
Plate and frame heat exchanger uses alternating A and B plates to separate hot and cold fluid streams. Fluids enter and exit through nozzles on the end frames. Gaskets act as a sealing system to prevent leakage and mixing. Upper and lower guide bars maintain plate alignment during operation. This design is very efficient for applications requiring compact and easy-to-clean equipment.
Thermal resistance in double pipe heat exchanger. Heat transfer in a double pipe heat exchanger can be modeled as a series of thermal resistances. These resistances consist of convection on the inner side, conduction through the pipe wall, and convection on the outer side. The magnitude of the resistance depends on convection coefficients, surface areas, and material properties. The smaller the total thermal resistance, the larger the heat transfer rate. This concept is very important in heat exchanger analysis and design optimization. Check your understanding number 3. This section again emphasizes the relationship between thermal resistance and heat transfer efficiency. The question is designed to ensure that reducing thermal resistance improves system performance. This is a direct consequence of the thermal resistance network model. This understanding is important before moving to overall heat transfer coefficient calculations. This short evaluation strengthens students' physical intuition. Heat transfer surface areas in double pipe heat exchanger. Heat transfer occurs through the inner and outer surface areas of the pipe. For thin-walled pipes, these two areas are approximately equal. Geometric parameters such as inner diameter, outer diameter, and pipe length strongly determine the device performance. Heat exchanger design often aims to maximize the effective surface area. This concept shows the direct relationship between geometry and thermal performance. Heat transfer coefficient range. This slide shows that heat transfer coefficient values vary widely depending on the type of fluid and process. Water-based systems have relatively high coefficients compared to gas-based systems. Gas-to-gas heat transfer has the lowest values due to gas physical properties. Special applications, such as steam condensers, can have very wide ranges. This information is important as a first guideline for design estimation. Fouling in superheater tubes. Fouling occurs due to the accumulation of particles such as ash on tube surfaces. This layer adds thermal resistance and reduces heat transfer effectiveness. If not controlled, fouling can cause overheating and performance degradation. Therefore, regular cleaning and maintenance are necessary. This fouling concept must always be considered in long-term heat exchanger design. Representative fouling factors. This slide shows that each type of fluid has a different tendency to cause fouling.
Distilled water at low temperature has a very small fouling factor. In contrast, engine exhaust gases and fuel gases have the highest fouling factors. Oils and refrigerants fall in the intermediate range. These data are important to include safety margins in heat exchanger design calculations.
Correct answer, C. Engine exhaust gases and fuel gases with fouling factors up to 0.0018 meters squared Kelvin per watt. Explanation of incorrect options. A. Distilled water below 50 degrees Celsius with a fouling factor of 0.0001 meters squared Kelvin per watt. This is incorrect because distilled water has the lowest fouling resistance, making it unsuitable as a candidate for the highest fouling factor. B. Oils and refrigerants with fouling factors ranging from 0.002 to 0.009 meters squared Kelvin per watt. This is incorrect because while these fluids exhibit moderate fouling resistance, their fouling factors are significantly lower than those of engine exhaust gases. D. Water-based fluids generally used in low-temperature applications. This is incorrect because water-based fluids, especially at low temperatures, typically have low fouling resistance compared to high fouling fluids like engine exhaust gases.
Nusselt numbers for laminar flow in annuli. The Nusselt number is used to represent the intensity of convective heat transfer. For laminar flow in annuli, the inner surface Nusselt number decreases as the inner to outer diameter ratio increases. In contrast, the outer surface Nusselt number remains relatively constant. Under symmetric conditions, both surfaces have the same Nusselt number. This information is important for detailed analysis of double-pipe heat exchangers. Temperature change in equal capacity streams. When the heat capacity rates of both fluids are equal, their temperature changes will be equal in magnitude. This results in symmetric temperature profiles along the heat exchanger. This condition applies only if the system is well insulated from the surroundings. This concept is very useful to simplify energy analysis. With this assumption, the relationship between inlet and outlet temperatures becomes easier to understand. Temperature profiles in condensers and boilers. In a condenser, the hot fluid undergoes a phase change, so its temperature remains constant during the process. In contrast, in a boiler, the cold fluid that boils maintains a constant temperature. Heat transfer in both devices is dominated by latent heat. This produces temperature profiles that are very different from ordinary heat exchangers. This understanding is important for analyzing phase change systems. Parallel flow heat exchanger temperature variation. In parallel flow, both fluids enter from the same side and flow in the same direction. The hot fluid temperature drops rapidly, while the cold fluid temperature rises rapidly. As a result, the temperature difference between the two fluids decreases along the length. This limits the total heat transfer potential. Local analysis shows that the heat transfer rate depends on the local temperature gradient and differential surface area. Check your understanding. Number 5. This section again emphasizes that a decreasing temperature difference will reduce heat transfer efficiency. The question directly connects the temperature profile to device performance. Students are expected to realize that flow configuration strongly determines the result. This concept serves as a bridge toward comparison with counterflow. This evaluation reinforces the physical logic of the temperature graphs. Parallel versus counterflow heat exchangers. This comparison shows the fundamental difference between parallel flow and counterflow. In parallel flow, the temperature difference decreases quickly, resulting in lower efficiency. In counterflow, the temperature difference can be maintained at a higher level along the exchanger. The inlet and outlet temperature difference expressions are also different for both configurations. This concept forms the basis of the LMTD method. Counterflow heat exchanger, temperature variation.
In counterflow, the two fluids move in opposite directions, so the temperature gradient remains high. The hot and cold fluids exit with a larger temperature difference compared to parallel flow. This allows better utilization of the heat transfer potential. The temperature profile shows a more uniform distribution along the length. This is the main reason why counterflow is often chosen in design.
Heat transfer in cross-flow multi-pass exchangers. For heat exchangers that are not purely parallel or counterflow, the LMTD concept with a correction factor F is used. The LMTD value is calculated from the inlet and outlet temperature differences of both fluids. The correction factor accounts for deviations from ideal flow patterns. The heat transfer rate is determined by U, A, F, and delta TLM. This approach is very important for analyzing shell and tube and cross-flow heat exchangers.
Check your understanding number 6. This section tests the understanding of the physical meaning of LMTD. The question emphasizes that LMTD is calculated from the inlet and outlet temperature differences of the fluids. This concept ensures that the calculation does not rely on a single temperature difference value. LMTD represents the average driving force for heat transfer. This understanding is very important before using correction factor charts. Correction factor F for heat exchangers. The correction factor is used to adjust the LMTD value for heat exchangers with non-ideal flow patterns. In shell and tube exchangers, the F value decreases as flow imbalance increases. For cross-flow with unmixed fluids, F values tend to remain high. When mixing occurs, the F value decreases and thermal performance is affected. These charts are very important in practical heat exchanger design.
Maximum heat transfer in heat exchanger. Maximum heat transfer occurs when one of the fluids undergoes the maximum possible temperature change. This value is determined by the minimum heat capacity rate and the maximum temperature difference between the inlet fluids. This concept defines the upper limit of heat exchanger performance. In effectiveness analysis, this value is used as a reference for the actual heat transfer. In this way, the device performance can be evaluated relatively.
Equal capacity rates in heat exchanger. If the heat capacity rates of both fluids are equal, the temperature rise of the cold fluid will be equal to the temperature drop of the hot fluid. This is a direct consequence of the energy balance. This condition produces symmetric temperature profiles. This concept is often used to simplify theoretical analysis. This understanding also helps to check the reasonableness of calculation results.
Correct answer, B. The temperature rise of the cold fluid equals the temperature drop of the hot fluid, ensuring balanced energy exchange. Explanation of incorrect options. A. The temperature drop of the cold fluid is always greater than the temperature rise of the hot fluid. This is incorrect because when the heat capacity rates are identical, the temperature changes of the two fluids are equal, not unequal. C. Heat transfer is unaffected by the temperature changes of either fluid, focusing only on flow rate. This is incorrect, as heat transfer is directly proportional to the temperature changes of both fluids, not just the flow rate. D. The heat exchanger achieves maximum efficiency regardless of its configuration. This is incorrect, because achieving maximum efficiency depends on the design and configuration of the heat exchanger, not solely on the equality of heat capacity rates.
Effectiveness, relations for heat exchangers. Effectiveness is used to express how close a heat exchanger performs compared to the ideal case. For double pipe exchangers, the counterflow configuration is always more effective than parallel flow. In shell and tube exchangers, effectiveness increases with the number of passes. For cross-flow exchangers, whether the fluids are mixed or unmixed strongly affects the effectiveness. This concept forms the basis of the effectiveness NTU method. Effectiveness versus NTU for heat exchangers. This graph shows the relationship between effectiveness and NTU for different configurations. For the same NTU, counterflow gives the highest effectiveness. Parallel flow shows the lowest performance, especially at large NTU. Crossflow lies in between, depending on the fluid mixing condition. This chart is very important for selecting the heat exchanger type in the early design stage.
Effectiveness versus NTU for configurations. This comparison again confirms the thermal performance ranking of different configurations. Counterflow is always at the top because it utilizes the temperature difference most effectively. Crossflow with unmixed fluids is in the middle. Parallel flow is at the bottom because it quickly loses the heat transfer driving force. This ranking is very consistent under almost all operating conditions. Check your understanding. Number 8. This section reinforces that the highest effectiveness is achieved when the temperature difference is utilized maximally. The question guides students to recall the main characteristic of counterflow. This concept links the effectiveness NTU chart to its physical meaning. In this way, students do not only memorize the curves, but understand the reason behind them. This evaluation strengthens conceptual understanding. Effectiveness for C equals 0 heat exchangers. For the case where one fluid has infinite heat capacity, the effectiveness formula becomes very simple. The effectiveness depends only on NTU and increases exponentially. This condition represents the theoretical performance limit of a heat exchanger. Although it rarely occurs in a pure form, this case is very useful as a reference. This concept helps in understanding the general behavior of heat transfer systems. NTU relations for heat exchangers. NTU relations depend on the type of heat exchanger and its flow configuration. For double pipe exchangers, the NTU value is determined by effectiveness and heat capacity ratio, with counterflow always performing better than parallel flow. For shell and tube exchangers, NTU is calculated based on one shell pass and then extended to multiple passes using a correction factor. For cross-flow exchangers, NTU relations differ between mixed and unmixed fluid conditions. This concept completes the overall effectiveness NTU method framework.
Correct answer B. Crossflow with unmixed fluid configurations because of enhanced heat transfer potential. Explanation of incorrect options. A. Parallel flow in a double pipe heat exchanger due to uniform effectiveness throughout. This is incorrect because parallel flow is generally less efficient than counterflow, and NTU values are lower for parallel flow configurations. C. Shell and tube with multiple shell passes, independent of the correction factor FFF. This is incorrect because the correction factor FFF significantly impacts NTU calculations in shell and tube heat exchangers, especially for multiple passes. D. Counterflow in a double pipe exchanger because the capacity ratio is irrelevant. This is incorrect because the capacity ratio CCC is a critical parameter in determining NTU and effectiveness, even in counterflow configurations. Counterflow is effective, but not the highest in all cases.
References. This slide lists the main sources of figures and materials used in this chapter. The primary reference comes from the book by Chengal and Gajar on heat and mass transfer. This shows that the material is based on internationally recognized standard literature. References are very important to maintain scientific accuracy and consistency. With this, the entire discussion of the heat exchanger chapter is complete.